as I mentioned in this slide, we need to exploit the data use behavior. So to do that, we exploit broadcasting structure. So let me explain the broadcasting structure.
The three of the number is correct.
Yeah, thank you. Thank you. Yeah. So let's see one example from Kai's. So they presented a chip having neural processing engine. Here, each engine consists of 32 max. This will have 32 max. So let's see how it works, exploiting the data use behavior for broadcasting. Let's see two-dimensional convolution. Here we have input data, and we have 3 by 3 columns. Let's assume that we have only 8 max in this example. So we have stacks of max, 4 max and 4 max. And each max is in charge of one output. So this one computes the output here. So in the first clock cycle, we fetch this data from on-chip memory, and these data from on-chip memory. And this one, for instance, uses this weight and this data, because this one is in charge of this one. And in order to obtain the result, we have 9 multiplications. Now we do the first multiplication among the 9, right? So here, we already see the case of broadcast, because these kernel weights are used by 8 max. In other words, we broadcast this data to 8 max. However, we don't broadcast the input data, not yet. We will do that in the end. Let's see what happened in the next clock cycle. In the next clock cycle, we will fetch this data, and we will fetch this one to this map. And we will add the result together with the previous one in order to have partial sum for this. Still, we broadcast this data to 8 max. So after 9 clock cycles, we can obtain 8 outputs, right? So what is missing here is we couldn't reuse the input data. That's what we want to do in the next slide. In order to reuse the input data, the solution is quite simple. So we already saw this case, right? We have 3 more such cases. And then by fetching one input data, actually this one is used here, 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 and here. We broadcast the input data to 4 max in this direction. Input data are broadcast in this direction, and weights are broadcast in this direction. So in this example, one input data item is reused 4 times, and one kernel weight is reused 8 times. So if you increase the number of max here, or the number of rows, you can exploit the reuse behavior. You can more exploit the reuse behavior. That's the basic approach of using broadcasting structure to use the reuse behavior. So almost all the hardware accelerators try to use such a broadcasting mechanism. And on top of that, we try to exploit value locality, especially 0 values. So you already know the pruning, but this slide shows pruning in human brain. So in the case of human brain, we have pruning, as you know. But one interesting fact is the number of synapses, the number of neurons, is at the top when the baby is 2 years old. So, but after that, we start to lose neurons and synapses. The same for the artificial neural network. pruning is to have sparse one from dense one. So as you know, the pruning is iterative process like this. After the training, if you obtain weight distribution, the pruning is to force small weight to zero, right? And then you retrain the network, and retraining actually changes the distribution like this. Finally, you will have the distribution with two modes like this. And then you continue to do the same thing, pruning, retraining. So according to these papers, like Songha's paper, we can significantly reduce the amount of weight because we have only to store non-zero weight. So by applying some additional technique like compression, Hoffman coding, we can reduce the amount of weight. But our goal is we want to reduce the execution cycle when we run through the model. So pruning is becoming more and more popular according to Songha's recent paper. We can exploit the prune results in a different way. So in this paper, after the pruning, we will have distribution like this. It's this one. Here we have a significant amount of zero weights. So we have two options. By exploiting zero values, you can save energy consumption, you can reduce runtime. But we have another direction. We can revive the pruned weight like this. So we give very small random values to the zero pruned weights. And then we continue to train the network. But after that, we will have weight distribution, something like this. What's the benefit? This one gives better accuracy than the original. That's what he found in his paper. Very interesting. So anyway, we have one more option with proved network. We can exploit zero values, or we can revive zero weights for better accuracy. So in the following slides, we will see the possibility of exploiting zero values. So the first hardware accelerator exploiting zero weights with memory contacts. So this figure shows very simple case. So here, we already pruned the connections. So we don't have connection here. This connection was pruned. In order to obtain the result here, we have only to do 2 multiplications. Right? Here 5 multiplications. Let's assume that our hardware accelerator has 4 multipliers like this. In this case, in order to obtain the result for this, we already have the non-zero weights here, so we have only to fetch B0 and B4. Right? So here the key message is we don't have to fetch all the data. We have only to fetch the data corresponding to non-zero weights. By doing that, we can reduce the amount of fetched data. Right? So for output 1, we need 2 clock cycles because we have 4 multipliers in this example. But we need 5 multiplications. So the performance improves as we prune more weights, right? So as if we have more and more sparse model, speed up increases. But in reality, according to Songha's paper, for instance, usually we can prune 65% of weight. So 65% of zero values can be translated to 3 times speed. Right? So the typical range is here. That's the story of weight pruning or performance improvement. Let's see another type of pruning, not the pruning, exploiting zero values. So we apply ReLU function to the result of convolution. But as you know, ReLU function gives zero value for negative results, right? That's why we have a lot of zero values in activation. So the ratio of zero activations. So we should be able to use them to reduce runtime and energy consumption. But in the conventional architecture like now, for instance, in that case, it was very difficult to exploit randomly scattered zero values because we distribute the input data to multiple processing units. So we can skip the execution cycle only when, in this case, both values are zero. But usually we have 16 wait. So the probability of having 16 zero values here is very low. So practically we cannot exploit zero input in such an architecture. So in the case of convolution, their naming is very interesting. They remove all the zero in the convolution. So in convolution, they broadcast only one data. So in the case of now, they broadcasted a group of data. That was the source of problem. But in this case, they broadcast only one data. So if the data is zero, they don't broadcast that data. Instead, they broadcast the next non-zero. We don't waste the cycle. We don't apply clock gating. We just skip the multiplication. And we send the next non-zero activation. Let's skip that. So they slightly modify the organization of how they accelerate. But after reading those papers, my students' response was very simple. Can we extract both zero values in waits and activation at the same time? Because Cambridge X can exploit zero waits, convolution can use zero activation, but there was no accelerator which uses both values at the same, both zero values at the same time. So this is our starting point. Here, the ratio of zero waits after tuning like this, and the ratio of zero activation after Lalo function like this. So we want to exploit both types of zero values. So here, in the case of Cambridge X, we exploit zero values. So here we have zero values, zero corner rates, and zero corner rates. So the processing element, this one will take runtime like this one runtime like this. So the total runtime is proportional to the amount of non-zero weights, right? In the case of convolution, the total runtime is proportional to the amount of non-zero activation. So in our case, we want to make the runtime proportional to the intersection of non-zero inputs. Intersection, that's the key. So here we have intersection here, here, and here. So we want to have the result like this. But after obtaining this, we found a new problem. Load imbalance problem. So this one, P1, PE1 finished earlier than P0. Why? This one had small work to do, right? Small work here. Actually, if we see the amount of non-zero corner weights, this one has smaller amount of non-zero corner weights than this one. So we have new load imbalance problem. So we call this problem zero-induced load imbalance problem. Actually, Cambridge X had the same problem because the runtime was proportional to the amount of non-zero weights allocated to each processing element. So in order to resolve this problem, our solution is quite simple. I will explain later. So our hardware accelerator looks like this. Actually, our architecture is based on Iris. MIT's Iris architecture. So we have two-dimensional processing elements, array and SRAM, and hierarchical bus. Let's see processing element first. So inside of the processing element, we have MAC, multiplier, pipeline multiplier, and adder, and some partial sum buffer. And we have input buffer. In our solution, we need input buffer in order to select non-zero pairs. So here, we have only 2 non-zero pairs among 6 pairs. So in order to do multiplication, it takes only 2 clock cycles by finding the non-zero pairs. In order to ease the process of finding non-zero pair, instead of using comparator, actually we use zero bit vector. So when SRAM broadcasts data or weight to the processing element, together with the date, we also send small size zero bit vector. By using that zero vector, the processing element do not have to compare that value with zero. So it has only to use that zero value. So by using 2 bit vector, we can easily localize non-zero pairs. So we do computation only for them. But real problem was data distribution. So it was not easy in the beginning to understand how. So this is our current solution. So here we have 3-dimensional input data. And in this example, we want to compute 8 output feature map because we have 8 sets of corner weights. We want to compute 8 output feature map using 3-dimensional input data. The first step is we divide the input data into, in this example, 2 parts. So actually, we divide the spatial dimension like this. So we call this one working group 0, working group 1. And then we further divide each working group into sub-working group. The reason why we have further division is here we assume that we use 4 processing elements. So originally we need to calculate 8 output feature maps. But if we have only 4 processing elements, so in that case we need to divide working group into 4 and 4. So actually we run them in parallel. After finishing this, we run computation in parallel for this. So sub-working group is mapped to a group of processing elements later. And then we further divide sub-working group like this. The reason is quite simple. The processing element consists of MAC and output buffer, and it has also small input buffer. Here the key point is small input buffer. It can handle small amount of data at any time. So it can receive small amount of data. So this amount of data, actually this one is the size of input buffer or processing element. So now we are ready to do parallel processing. So we will come back to this. Let's see how we can broadcast data and weights. So first, we broadcast weights. So here in SRAM, we have weights, and we fetch one corner weight, and we broadcast that data to different processing elements. The reason why we can broadcast this corner weight to different groups is we have spatial dimension division. So in other words, we use the same corner weights in both cases. So we can broadcast corner weights in this way. So you may understand the difficulty of such an animation. So you will see more difficulties soon. I didn't do that. My students spend a lot of time. Yeah, so he spent 2 or 3 days in France. Actually, he presented his paper at 8 this year, but fortunately at the last day of 3-day conference. So for the first 2 days, he spent all the time to prepare. So we broadcast the data like this here. So to 4 processing elements, we broadcast the same data, here the same data. We exploit the broadcast. But convolution operation requires moving the window, right? So the new window overlaps the previous window. They have significant data, significant amount of data in common. So in other words, we have only to fetch small new data, right? So this part represents small new data. You will see soon. This one, small new data. We need to fetch them from on-chip memory to processing element in the same manner. So in this way, we perform direct convolution actually. So for the first sub working group, we can compute 4 output feature maps, and we move to the next sub working group in order to calculate the remaining output feature maps. And I mentioned that we have a new problem, zero induced load imbalance problem. So this figure shows the problem. So let me explain our solution. Yeah, so our solution is, I will come back to this slide again. Let's see the problem graphically. So this one shows the load imbalance. So vertical bar represents the number of clock cycles actually. So we run multiple processing elements in this granularity. We run multiple processing elements here. And then we run multiple processing elements here. So the difference here represents the amount of load imbalance. So, but as I said, a part of load imbalance comes from the different amount of non-zero weights on the processing elements. So our solution is quite simple. We sort the sets of corner weights in the increasing order of the number of non-zero weights, like this. And then we run corner weights in this manner. So here we run corner weights like this. So their load imbalance gets significantly reduced. So simply speaking, as in the case of Wiener-Gregg convolution case, where we reorder the expression, actually we reorder the expression, considering the number of non-zero weights. So the previous slide, yeah.
So you reorder the kernel, not the irregularity in data.
Yeah, sure. Yeah, it incurs some irregularity. Yeah, sure. But we touch the corner parts, which means we can handle that irregularity in design time. We can prepare the new execution order in design time here.
Yeah, I think that's okay.
Yeah.
Order the kernel part data.
Yeah.
The data from the memory.
Yeah.
becomes
Yeah.
irregular.
Yeah, it becomes more irregular. But in our case, we assume that we use a relatively large option memory. So we fetch all the data of one layer, all the input data of one layer into the on-chip memory. So in the case of on-chip memory, irregular memory access does not incur a significant problem. But in the case of off-chip memory, yeah, it will cause significant problem. So in our analysis, we considered all that kind of defects in estimating energy consumption of SM size. So our method can be explained using this example. So originally, here, let's assume that we have two processing and two max here. So, yeah, maybe this one is the problem. Okay. So originally we mapped the kernel sets K0, 1, 2, 3 in the index order. That's typical way. So this one here, this one here. So in that case, we have load imbalance problem. So this one finishes much earlier than this one. Same here. So in order to improve the situation, what we do is we just reorder them and we map them like this. Now load imbalance problem still exists, but we have less load imbalance than before. So we evaluated our idea by designing two versions of the hardware accelerator. One is 16-bit fixed point version, the other one is 5-bit logarithm computation version. Using this environment, we did quick layout in order to have better timing and power estimation. And our baseline is iris. So we did ISO area. We assume the same chip area, the same technology, and we try to compare the energy consumption and runtime. So as you can see here, they have similar amount of watching memory. And here, the processing PE group size actually. So this size represents the amount of broadcast operation. So by fetching one data, actually we broadcast the data to 33 processing units in this case. But these numbers depend on the data size and model and conversion layer. So we did manual design optimization for this. This is the key result. So our baseline is iris. So iris gives speed up of 1 here. So by exporting 0 weights and 0 activation and both, we could achieve this level of speed up. And by resolving the load imbalance problem, we could obtain additional improvement. So 4 times speed up in the case of LSD, and 5 times in the case of BDT. This figure shows per layer speed up analysis. As you can see here, the third convolution layer gives the largest speed up. This table shows why. So the third one has the highest ratio of 0 weights and 0 weight. Highest ratio of 0 weights and high ratio of 0 activation. That's why. However, in the case of the first convolution layer, the speed up is very small. The reason is also explained here. So this one takes the low image. In the low image, we don't have 0 value, technically. And the first layer is very sensitive to the optimization. So it's quite difficult to prune weights. So we have very small amount of 0 weights. That's why. So for the other layers, we can obtain large speed up. The energy consumption, in our case, we didn't apply other techniques like compression using 0 value. That's why we could not reduce the energy consumption due to SRAM and buffer. We could reduce only the logic part. Yeah. Actually, we did RTL design using Verilog. Verilog RTL design, and we did chip layout using Synopsys Astro. And we used this tool for gain level power estimation. So they are based on gain level power estimation. After the first layout k-level power estimation. But for the on-chip memory part, we use typical model called CAC type. But for the logic part, we use first layout k-level simulation. We also designed a 5-bit version by using logarithm-based quantization. So this figure shows the effect of narrow data. So by using 5-bit data, we can reduce the energy consumption significantly. Actually, for the given chip size, actually we can increase the number of max, so we can improve the performance significantly. Actually, 5-bit version gives 10 times performance improvement compared with the baseline.
So in by simulation, you keep training, that will take a lot of time.
No, we don't do training. We use trained model. So actually we receive the pruned model from Song Han, and we use his pruned model.
So the input data is even.
Yeah, input data, for the input data we use ImageNet data. We applied 1,000 ImageNet data by randomly selecting 1,000 ImageNet data, and we ran the simulation. Yeah, it takes long time. Even though we have architecture simulation and we also do Verilog simulation, it takes long time. A few days. Yeah. No. Baking chip is another story, as you know. Yeah. So actually we did similar thing on FPGA. Yeah. So we have full FPGA chain. Chain from cafe down to FPGA. So after that, we did an additional optimization. So actually we found another source of load imbalance between the working group. Actually, if here we have many zero values, this one will finish the job earlier than this. So we have that kind of load imbalance. So we applied work stealing, the traditional work stealing method. So this is the final result. In the case of AlexNet, 4.4 times speed up. In the case of BBG, 5.6 times speed up by exporting zero values. And recently, NVIDIA presented their zero-aware hardware accelerator called sparse CNN. So we compared ours with sparse CNN. This is a summary of sparse CNN. And this is the overall structure of sparse CNN. The basic idea is quite nice in the beginning. Very nice. But at the end, we see the difficulty in real design. So in the beginning, they do Cartesian products of non-zero weights and non-zero activations. That idea is very nice. However, the problem is, after obtaining 16 multiplication results, we need to find their destination. Actually, we need to manage partial sum here. To do that, we need very small SRAMs here. But as you know, small SRAM is bad in terms of area efficiency and power, right? And we need some crossbar. So actually this one, even though the size of this is, the capacity of SRAM here is 6 kilobyte, and the capacity here 20 kilobyte, so the area for this occupies 40% of processing area. So that's why they lose some efficiency, even though they have some other reasons. So we compared the two solutions. So here our solution, this one here is 4.4 times speed up. But in their case, they obtained only 2.4 times speed up. So we tried to understand why, and according to the paper, they explained why a little bit. So the problem can be expressed with the utilization of multipliers. So here, in the case of AlexNet, for instance, So convolution 3, 4, 5 have low utilization of multiplications. That's the source of problem in the case of sparse CNN. So here I summarize the reason why they have low utilization, actually into the sparsity. And we also compare the two in terms of ISO area comparison. And we found that ours can give some advantage to the SCNA. So until now we covered accelerators for convolution operation. But in reality, especially for servers, according to recent Google paper on TPU, MLP dominates server workload. So MLP looks like this, simpler than convolution. So in order to obtain the result here, we use all the inputs and each edge has its own weight. So we do dot product operation, we have this one. And in order to have this one, actually we do matrix vector multiplication. So matrix vector multiplication is the key in NLP and RNN.
So it's just a fully connected.
Yeah, fully connected layers. So as I mentioned, we have matrix vector multiplications. So TPU version 1 is for matrix multiplication. I will explain why we have matrix multiplication. So according to Google's TPU paper, we can see this table. The key part here. At this time point, 60% of server workload is due to MLP, and 30% SPI. Only 5% CNN. So this is the server story. On mobile, embedded system, we have totally different story. Convolution dominates. But in the case of server, they have very different story.
This data is also 9 years old, right?
Not 9, yeah, actually only 3 years old.
So.
Yeah, this is another story. Yeah, that's what I wanted to explain. Yeah, so the reason why I put the title of the paper title, this one, is why we need MLP on server. For what? This paper explains a little bit. According to this paper, MLP is quite useful to find good product recommendation for a user. Let's assume that you visit Amazon website. If you are a frequent visitor there, immediately after you enter their website, you see recommended product for you, right? To do that, they use MLP, according to this paper. But there will be many secrets, but according to this paper, you can guess that MLP may be for the kind of product recommendation. So they design matrix multiplication accelerator. So here they have 256 rows and columns. So in total, 64K multipliers. In terms of the number of multipliers, this one gives more multipliers than NVIDIA's recent Tensor Core, right? But here they use 80 multipliers. The key part is here, actually. So here they fetch the data in this direction from on-chip memory. So in the case of on-chip memory, it's relatively easy to have high bandwidth by sacrificing some chip area. But in the case of off-chip memory, very different story. Pin limits the bandwidth. So in that case, they use DDR3. So the memory bandwidth was 30 gigabytes per second. So we have asymmetric bandwidth capability. Here, high memory bandwidth. very low memory bandwidth. So the performance is determined by this one. So if you can increase the bandwidth here, you can improve performance. I will explain why in the following slide. So here, what they want to do is matrix-matrix multiplication. Okay. So this is chip program. And they do matrix-matrix multiplication in a systolic manner. So if you consider the multiplication of two matrices, and you can send columns of data in this direction and rows of data in this direction, you can easily identify how it works. It's not difficult. So historic orientation is not a difficult way. But the problem is, as I mentioned, after designing the DPU chip, they changed some key parameters. But the performance did not change, except this case. This one, memory bandwidth. As I mentioned, memory bandwidth is the bottom in their design, as you can see here. So why? The story starts from matrix spectrum multiplication. So MMP requires matrix spectrum multiplication, right? So in this case, each weight is reused only once, right? But the size is huge. According to their paper, the size is huge. So that's why we can store these data only in option memory. But by fetching these data, we use them only once. That's matrix vector multiplication case. However, we can mitigate, or we can improve the situation. How? By introducing large batch. So that actually they also use large batch. Large batch means they have the same matrix part, but they have multiple columns of input data. So now matrix vector multiplication becomes matrix multiplication, right? Like this. Now we have matrix multiplication because we have multiple columns. So the number of columns is the batch size. So they use 200. But the problem still remains. I will explain why. So they have 256 by 256 arrays, right? Which means even though we have very large matrix here, matrix multiplication can be done at this granularity, right? Because they have 256 array of multipliers. Right? So here we can provide the data here. We can provide the data here. So as we saw in the previous slide, what we do is actually tiling again. So 256. We do multiplication for this type. As we saw tiling in the case of two glass, right? So we need to apply tiling. So in the case of tiling, anyway, the weight data are stored in option memory. So in order to execute the tiling operation, we need to fetch the data from the option memory, right? So let's assume that we finish the operation for this type, and we move to the next type. What we need to do is we need to fetch this data from the memory, right? So that path is here. Here. The bandwidth is only 30 gigabytes. But here, we have high memory bandwidth. If you check this, so actually here we have 256 columns. So we need to provide 256 bytes in parallel every clock cycle in order to have 100% utilization of multipliers, right? If you consider the clock frequency, 0.1 gigahertz, the required memory bandwidth here is 179 gigabytes per second. This one is okay. Similar, approach this level. But this one is far below this level. That's why if you increase this part, improve this part, the performance increases linearly. So that's why they need high memory bandwidth solution like HBM2, 3. But there's another way to address this problem by exploiting pruning, right? So I found these figures from Sohan's ISCA paper last year. So in the case of MLP, we can apply pruning. And pruning can give significant amount of non-zero, significant amount of zero weights in matrix. So we can reduce up-to-memory traffic. And we can process such sparse matrix multiplication using specialized hardware accelerator like this one. That's what we can do. So we are here. So let me summarize my lecture, giving you my prospect. So the keywords, two keywords that I want to share. One is always on AI. So in these films, actually the AI assistants run on server, right? But what we want is some assistant running on our smartphone or our embedded devices. Let's see one very simple example. When we see our baby smiling like this, usually we want to take a picture, right? But in order to take a picture, first we need to turn on the smartphone and we need to find camera app, and it's gone, right? So what we need is maybe something like this. If you have smartphone, if you see this one, like this. But in order to realize this idea, we need some function like always on AI. Not always on, but some special function. So that's object detection is the key part here. So the smartphone should detect the gesture of your hand movement, and it should turn on the camera. After that, it should determine the focus, right? To do that, it should do some object detection. And after finding objects, it needs to make a choice among multiple objects. If you are in your living room, maybe the target will be your family members. So it can focus on the baby. That kind of operation should be done very fast with low power. Another example of always on AI is maybe that kind of application is running implicitly, as my guess. But your smartphone can listen to everything you speak. It's real always on AI, right? So it can understand what you said in the whole day. So, but in order to enable such an always on AI capability, the bottleneck is energy consumption, especially in the case of smartphones. So we need to exploit all our knowledge. Algorithm optimization, other optimizations, and circuit level optimizations in order to reduce the energy consumption. So currently, in the case of hardware accelerator, the power consumption level is typically 100 milliwatts or tens of milliwatts. But that is too high for always on AI function. We need less than 1 milliwatt operation. How? Algorithm optimization, circuit technique. If possible, better algorithm using automatic design method. That's what I want to share as the last topic. So here we see 4 representative neural networks: AlexNet, GoogleNet, SkizNet, and DigitalNet. But we don't know how the authors of these papers devised these networks. We don't know the secret, right? That's why recently there are some papers on automatic synthesis of neural network architecture. So I'd like to share 2 papers in the following slide. In this case, you can generate the configuration of each layer. So the spatial dimension, the number of feature maps, stride size, something like that can be generated by this tool. After the generation, you train the network. And then you can evaluate the quality of generated network in terms of error, right? And then you memorize the results using, in this case, Q-running. Weighted sum using some data. In another approach from Google, they use recurrent neural network to generate such parameters. So recurrent neural network is good to generate some character string. So they exploited that feature. So as you can see here, this one generates some parameters, filter height, width, and something like that for one layer. And they move to the next layer. And then they evaluate the generated network after training. And with reinforcement learning, they improve the RNN, or the parameter combination. This is the last slide. So, what's the quality of generated network? In the case of small size model, like Cypher10, the quality of generated model is comparable to the best human design. But this is for small model. For a large model, we have much larger design space to explore. So it may not be easy. However, in the case of always-on AI, we don't need large network, right? We need very small, optimized network. So maybe we can apply this kind of idea to design optimized neural network for always-on AI. Yeah, this is the summary slide. So we covered some optimization methods, including algorithm level optimization and mathematical solution, and quantization, and tuning, and some prospects. Thank you for your attention.
Any questions? Yes, please.
Thank you for your help. I have one question regarding accelerator or May 2017. As I know, Iris architecture use row stationary policy that is split kernel into rows and transmit it to different keys.
Right.
Does your architecture keep this policy or?
No, we don't. Yeah. We don't use inter-processing element communication. Yeah.
So the entire kernel is one.
Yeah. One PE is in charge of one output difference.
demo day 之后啊，送明天大家准时到，因为我们第一场呢就是那个Iris 这个威廉斯教授 MIT video 进来，只有90分钟啊，他的讲义很多，所以你迟到的话会 miss 掉。明天注意多点以前就好吗？